Good afternoon, everyone. I welcome you on behalf of Epicon Friends of Concrete, a knowledge sharing platform since 1999. This works under umbrella of Epicons Consultant Private Limited, which is ISO 9001 2015 certified company, and one of the well-defined objective is imparting technical knowledge to the society and interested parties. Next. Our inspiration goes back to our friend, philosopher, and guru, late engineer A.P. Remedios. Because of him, we got inspiration to start such kind of a workshop series to begin with. Next. EFC has conducted 83 workshops in last 22 years and 43 webinars in last 4 years after lockdown. Started webinar series since lockdown through our unit EFC dedicated to training. The 2 photographs from 2 different workshops at actual physical work site. AFC is an humble effort to create knowledge sharing platform and develop a facility for continued education for practicing structural engineers, corporate consultants, government similar authorities, architects, builders, and of course faculty and students. Next. Our thought leaders. It starts with pre-Vice Chancellor and Principal of CGTI, Dr. V.N. Gupchup. It goes back to Professor Sundaram, who was HOD of Structural Department since I was studying there. Professor Garge is still with us and continuously helps us in organizing workshops and webinars. Dr. Sudhir Jain and Murthy were the first persons who invoked the interest in earthquake engineering. And Dr. P.C. Basu is the first person who delivered a lecture for us in Vizitia just before Gujarat earthquake. Next. And now Professor Dr. Yogendra Singh is a person for last 4 years who continuously helping and addressing all the interested parties and influencing all the engineers from different parts of India. Right now, we are on webinar 144, discussion on draft IS code 13920. Next, we are looking for physical workshop, Think Beyond Green, in September 2024 at Vizitia. Our team, apart from myself, Jayan Kulkarni, we have Mr. Anand Kulkarni, Mr. Ravindra Deshpande, Mr. Arvind Parolekar, Mr. Parashar Mugi, and Mr. P.P. Pandey as our team members who have major role in Epicons to play. And with this, I thank you all. Of course, any webinar or workshop means our entire office team helps in developing the entire process. Thank you very much.
Thank you, Jayan sir. Now I request Hemant Vadakar sir to introduce ISSE.
Can you see the screen now?
Yeah, make it full screen.
Okay. So welcome for this event arranged jointly by Epicons and Indian Society of Structural Engineers, that is called ISSE. So I welcome you all on behalf of Indian Society of Structural Engineers. Just I will give a brief introduction about ISSE, what ISSE is doing. See, basically this is an organization dedicated to structural engineering profession. And now all civil engineers are part of our team and they can become our members. Recently, ISSE completed 25 years. So we have celebrated the function of Silver Jubilee recently in VZTI. Now, what are the aims of ISSE? To afford the role and status of structural engineer in the construction industry with the awareness of professionalism, to define the boundaries and responsibilities of structural engineers commensurate with the remuneration. Again, ISSE is again coordinating with various government organizations, corporations, and similar other bodies all over India on behalf of its members. Now that again talks about the registration formats, the certification formats to be developed by different agencies. So ISSE is playing key role into this draft of certification formats. And of course, as Jen Kulkarni rightly said, to update our members on the latest developments in the field of civil engineering through various initiatives, like we have webinars nowadays, we have physical seminars, we publish technical bulletin also. So through this, we try to update the knowledge of our members. There are different areas of focus ISS is looking at. Structural designing and detailing is the most important part, of course. Then the computer software nowadays, which of course, without which we cannot do anything. Material technology, teaching and research development, this is also most important. We have to have interaction with academia, latest research, we should understand. Rehabilitation of structures is another big field nowadays. Latest construction techniques, that also we have to look at. Geotechnical and foundation engineering, environmental engineering. Non-destructive testing is another field, which is again very important nowadays. And then of course, bridge engineering and other related structures. This is a team at ISSE headquarters. We have our president, Mr. Shantilal Jain, myself secretary there, and I'm looking after the technical bulletin also publication. And Mrs. Mansi Nandgaonkar is looking after, she's the treasurer. So we are working in headquarters in Mumbai, but we have members all over India. And of course, we have local centers in different parts of Maharashtra and India as well. So this is a list of our local centers. So they also conduct the programs locally for their engineers. So that is the idea. And again, as rightly said by Jayan, it is a knowledge sharing platform. We look at it. So whoever has knowledge, whoever has some information, they can share it with us. We will share it with our fraternity. That is the aim, and that is the idea. Similarly, we have student chapters also in various colleges, engineering colleges in Mumbai as well as in other states also. So we have about 10 student centers right now, and we'll be expanding those in future. This is the idea, is to involve students also, and they should know what is going on in the field. So there has to be some interaction with the students. So for that purpose, we are just starting the student centers at various locations. So we have different type of memberships. We have one-time life membership fee. Minimum nominal membership is 5,000 rupees. So it is only one-time fee you have to just pay. So you will get all the invitations about programs. You will get the technical bulletin, which is published quarterly by ISSE. And again, we conduct a lot of, I think, lectures, seminars, workshops, webinars also. So this is a joint webinar now with Epicons on the very interesting and important topic. And as you know, Dr. Singh is also a very popular lecturer now in the forum. So on his name also, the registration gets full immediately. So you can just listen to him now about this today's topic as well. Now we again have a lot of publications based on our seminars and workshops. So these are available on our website also. You can go to the website and just have a look at that. We publish quarterly bulletins and journals. Again, it is a knowledge sharing platform. So we try to just share information with our fraternity. So if someone is doing some good project or some do's and don'ts and something interesting, so that we try to share. Under our Silver Jubilee function, which was held at ISSE some time back, we invited the code writers. So Ms. Alpa Seth also was there. Unfortunately, CVR Murthy professor could not come actually due to some unexpected reasons. But this was a big function we had at ISSE. That was on 1893 basically. Similarly, we have latest function on ultra high performance concrete, that is M160 concrete. So this is developed by Ultratech Cement. So they have just given presentation on that, how they have developed this and what are the applications of this. So again, I just appeal, this is as a platform we look at as social work. So keep learning and share your knowledge and experience with the fraternity and spare some time for the fraternity. Join hands to make our structures durable and sustainable, and which will also help in the nation building finally. So that is what I again appeal to all those who are not our members. I just appeal, please become our members and support ISSE. So you can just visit our website. There is online registration also possible. So thank you very much.
Thank you, Hemant sir. Now I request Parulekar sir to give preamble and introduce our speaker, Dr. Yogi.
Good afternoon to all friends. Welcome to webinar 144. discussion on draft IS code 13920 by Professor Dr. Yogendra Singh. As you may be aware, BIS has published draft second revision of the code IS 13920 on ductile design and detailing of RC structures subjected to seismic forces for wide circulation in June 2024 and asked for studied comments from the academia and professionals. The last date of submitting these remarks is 3rd August. Professor Dr. Yogendra Singh has been conducting physical workshops and webinars for Epicons Friends of Concrete for many years now on the topics related to earthquake resistant design and related topics, including the codal provisions and logic behind the clauses. Hence, we thought it prudent to organize an online discussion on this draft version of the code between the industry and him so that the collective remarks feedback can be sent to BIS. Today's webinar is the result of these efforts in which ISSE, Indian Society of Structural Engineers, is supporting us. Of course, during this discussion, we are going to listen from him about the rationale of various important existing and proposed clauses, which is going to be treated as always. We had asked for questions from the participants beforehand. We have compiled and selected relevant and important questions from them, which we will raise after the initial presentation along with those questions which are put on question answer platform. So friends, without taking any more time further, I would like to give you the formal introduction of Professor Yogendra Singh. Professor Dr. Yogendra Singh is currently Railway Bridge Chair Professor of Earthquake Engineering in IIT Roorkee. B in Civil Engineering from IIT Roorkee in 1989, MTech and PhD in Structural Engineering from IIT Delhi in 1990 and 1994 respectively. His research interests include performance-based design and buildings and bridges, inelastic seismic response of structures, seismic evaluation and retrofitting of structures, and soil structure interaction. About 30 years of research and teaching experience, guided 18 PhDs, published 85 research articles in various journals, and presented more than 90 papers in national and international conferences. He is member of several expert teams for post-earthquake damage surveys, convener of the BIS expert group on performance-based seismic design of structures. Collaborated with various universities across the globe like NORSAR Norway, NGI Norway, NTU Singapore, Stanford University USA, University of Edinburgh, UK, University of Windsor Canada, University of California US, and University of Porto Portugal. So with this introduction, I request Dr. Yogendra Singh to start his presentation. Thank you.
Thank you very much, Parlekar sir. And I welcome all the participants who have come this evening or joined with us on this important topic, which is going to affect the profession in the coming years. So I will first share my screen. And I guess you can see my screen now.
Yes, sir.
Change the settings. Yeah. So I think it's available now.
Yeah.
It's visible in full screen.
Yeah.
Okay. So friends, as Mr. Parulekar and other speakers prior to me have introduced, that today we are going to talk about the ongoing changes in the ductile detailing and design code, IS 13920. So there is a slight change in the name also. We were also discussing just before this, starting this today's session, that there is a change also, and actually it's a large program. It's part of a large program in which restructuring of different codes, because these earthquake codes have been developed at different times, and accordingly the numbers were somewhat haphazard. So what BIS is doing, we are bringing as part of this restructuring program all the force related codes together, which are dealing with the calculation of earthquake forces on different types of structures. Those are bringing together as part of IS 1893. So IS 1893 is proposed to have now 11 parts. and all types of structures, including general provisions, will be part of IS 1893. And these part numbers will remain same. And similarly, another set of codes will be under this number IS 13920. So parts will remain same. The structures which these parts will be dealing with will remain same. And in IS 1893, all the provisions related to calculation of the forces, earthquake forces on these structures, those will be dealt with. And in IS 13920, the design and detailing, in addition to the basic design codes. For example, in case of RCC, the basic design code is IS 456. So whatever is needed in addition to IS 456 from earthquake resistant design point of view, that will be covered by different parts of IS 13920. And these parts, most of these are yet to be developed. These are not still developed. At the moment, only two parts are available. Part 1, general provisions, and Part 2, buildings. And rest of these will come in due course of time. But a placeholder is kept so that whenever these codes are developed, those can become part of this series. So in IS 13920 Part 1, today we will discuss IS 13920 Part 1 and Part 2. And there are different sections in Part 1 and Part 2. Again, those sections also remain same. Those are dealing with the same type of structures. So for example, Section 1 is regarding the additional criteria for all structures. So as I said, this code is talking about additional criteria in addition to the basic codes. So every structure has a basic code. For example, in case of masonry, the basic code is IS 1905. And 4326 was also dealing with some of the provisions. So whatever provisions were there in IS 4326 regarding design of masonry structure, those have been brought into this code. And similarly, some special publications or other codes were published time to time. So those have also been brought under this single volume, which will consist of 4 sections. So Section 1 will be regarding additional criteria for all structures. Section 2 will be regarding masonry structures. And what changes are occurring, that is also mentioned here. So basically, the changes are occurring or the purpose of this revision is to harmonize these codes with the other available provisions. Some of those provisions are being made part of it, and some of the provisions which are beyond CD 39, the committee is different. There will be harmony between those. So there should not be drastic or contradictory provisions in the two codes. So that will be ensured through this revision. Then similarly for masonry structures, we are most interested in RCC structures, and today we will be focusing actually whatever clauses are there in Part 1 and Part 2 related to RCC structures, that we are going to focus in today's talk, because that is the most common type of construction in our country, and I guess that most of you are also interested in RCC structures. Steel structures are not that common, and masonry structures are generally non-engineer type of construction, or I will say pre-engineer. So the code will provide some prescriptive design guidelines which can be followed in masonry structures. So those we are not talking today, but if there is an interesting group, we can have a separate discussion on masonry structures. Similarly, there is additional criteria for steel structures also. You may be aware that ductile detailing code for steel structures was developed recently. So now we have ductile detailing code of steel structures, and that will also brought as part of 13920. So 13920 will deal with all types of structures and all types of materials of construction. Now in IS 13920 Part 1, let's first talk about Part 1, what this Part 1 is doing, and I will be highlighting here those provisions where the changes have been made with respect to the previous codes. So whatever changes are being made, I will try to highlight. And then after this presentation, we can have further discussion on these clauses as well as some other clauses in which you may be interested. So from the questions, I have discovered that some interest is there in the changes being made in IS 1893 also. So I'm not presenting the changes with IS 1893 because as informed by Mr. Parulekar, one session on that has been already done. So we are not discussing that, but if there is any specific question regarding IS 1893, also the revised or the draft version of IS 1893, we can take up that also. And we are focusing here only on those provisions where there is a change. Those which are similar to the previous codes, I will not talk about those. So in the scope, it has been clarified that what this IS 13920 Part 1 is catering to. So the purpose of this code is to enhance earthquake resistance of members and structures. And then this B has been included, use of base isolators and supplemental damping devices when buildings are designed to sustain limited damage. So a new term has been introduced here, buildings with limited damage. So our current design philosophy, as you are aware, the current design philosophy of earthquake resistant design is that the structure may get damaged. Now, how much damage the structure will undergo, that is also not quantified. It may be anything right up to the verge of collapse of failure. So our structure may be damaged to such an extent that it is just imminent to collapse. Then that type of philosophy may not be valid or may not be acceptable for all types of structures, especially critical structures and hospitals. So for those, this different design strategy using base isolators and supplemental damping. The code on base isolators is already there. It has already been published. You might have seen. Supplemental damping code has not yet been published, but this code is at least recognizing the need for these two codes. So these two will also be developed. I mean, supplemental damping part will also be developed in due course of the time. And many people confuse use of base isolator and supplemental damping with economy. So this is also clarified in this statement that use of base isolators and supplemental damping is not for achieving economy. It is for achieving better performance. That is limited damage. And the code also explains what is meant by limited damage. We will discuss that. Then perform capacity design of structural members and connections, because it is an important step in achieving the desired ductility. And when we are designing the structures to sustain damage, now please pay attention to this phrase, structures designed to sustain damage. What does that mean? It means the structures which are designed with conventional philosophy, which I was telling that such structures will definitely undergo some damage. How much will be the damage? That is a question which remains, but those structures will undergo some damage. That means those structures which are not designed for limited damage, all those structures have to be provided with capacity design so that those have adequate ductility. And then mitigate the effect of liquefaction. Liquefaction was earlier part of IS 1893. Now it has been made part of IS 1893 revised, as well as 13920. Also some clauses have been added related to liquefaction. Then these provisions are which are included in this standard are also related to methods of design for architectural and equipments and other units. So equipment, services, and architectural features, all these together, they are calling AEUs. All these AEUs, earlier our code was not dealing with these, but AEUs are having an important role in performance-based design of any structure. For example, if we are designing a hospital building, then the architectural and these ancillary units, other non-structural components, their performance is also important. And this is particularly stringent in context of hospitals and other critical structures. Then use of some of the building systems have been prohibited or restricted in some of the earthquake zones. So IS 1893 actually provides a table in which structural systems can be used in which zones. A table has been given. Although it is part of IS 1893 and not part of IS 13920, but I have taken that table from IS 1893, and we will spend a few minutes to discuss that also. So the designer has to choose the structural system as per that table. Now in IS 13920 part 1, two types of, as I said, two types of structural design approaches are there. One approach is low damage design approach, and another one is the damage in structural elements. So in case of low damage approach, no member of the lateral load resisting system shall sustain damage under effects of design earthquakes. So under DBE, all the members are expected to remain elastic. So that has now been quantified by the code. Earlier, it was not clear that when we are designing our structures, let us say using dampers or base isolators, then what we are expecting, what performance we are expecting. So that is now clarified by the code, that design we will be doing with this intention that under DBE our structures will remain, all the components will remain elastic. Only under MC level earthquake, some members will yield or will undergo damage. And this we can achieve by specially designed devices, which are provided at selected locations. And these devices will dissipate earthquake energy. And the structure will not require to damage itself to dissipate that energy. And that's how we will be able to achieve low damage. The conventional normal design, which we have been following, that is in the category of damage in structural elements. And it emphasizes that if we are following the conventional methodology, the damage is inevitable. So it has clarified the objectives of design using response control devices, base isolation and damping devices, and the conventional design. That's a major change in IS 13920 revised. Then the measures to mitigate effects of liquefaction at a site are also included. So many sites may be prone to liquefaction during earthquake. Earlier, we were not paying so much attention to liquefaction, but now the revised IS 1893 has given a lot of emphasis on design of foundations and geotechnical aspects, including liquefaction. So some part of that is included in IS 13920 part 1 also, and it provides two approaches to tackle with liquefaction. One is reducing the demand on the soil layer, which can undergo liquefaction, or increasing the capacity. So these techniques are put in two categories. So those which are reducing the demand are stone columns and piles. If we are providing, then we are reducing the demand, or we can enhance the capacity. For that, we have to enhance the compaction of that layer somehow, and that can be done through vibro compaction, vibro replacement, or surcharge. So if we are increasing surcharge somehow, then also the pore pressure which is developing will get counterbalanced, and the soil will not undergo liquefaction during that. Then, as I said, that architectural elements and utilities, these are given special emphasis in this revised code, both IS 1893 as well as IS 13920. So IS 1893 is dealing with the clauses related to calculation of demand on these structural elements and non-structural elements. Sorry. And in calculation of demand, we have to look into the acceleration at that floor level. So floor acceleration demand, and also the story drift demand. How to calculate that? That is dealt with in IS 1893. And then how to design for that demand? That is being dealt with in IS 13920. So IS 13920 part 1 provides earthquake protection strategy. So in case of AEUs, two types of devices are there, or rather two types of such utilities are there. One is acceleration sensitive. So acceleration sensitive are those which are generally located on the floor, and these are subjected to floor acceleration. And these can undergo overturning, sliding, or both. So some arrangement is to be made, some anchorage is to be provided so that these are not overturning and sliding. And then displacement controlled or displacement sensitive AEUs are those which are generally connected between two stories or two components of a building. So when these are being connected between two stories, these are subjected to drift, interstory drift between the two stories. And if these are connecting between two parts of a structure, then this is subjected to the relative displacement occurring between those two parts. So both these types of AEUs needs different type of arrangements to safeguard those during earthquake. And it is clarified very clearly, and this is very important, that any AEU shall not be secured to infill masonry walls. And the reason is that infill masonry walls themselves are prone to damage and collapse during earthquake. So whatever utilities we are having, those are to be connected with RCC components. So these are to be connected either to concrete or steel components of the buildings. We will not connect, whether it is acceleration sensitive or it is displacement sensitive AU, we will not connect it, to the masonry wall, because masonry wall itself is prone to damage during earthquake. Then in case of critical and lifeline structures like hospitals, special attention is to be given to these AEUs, and some restrictions are there. For example, false ceilings generally are restricted. We should not provide false ceiling in hospitals. If it is required due to medical regions in any portion of the hospital, then it will not be hung from the soffit of the RC roof. So it will not be hung from roof, because during shaking, this may get loosened from the roof and it may fall down. So what it has to be done, it has to be connected with the vertical RCC components or the beams. So it will be connected to the beams or the vertical components, but not masonry. It will not be connected with the RCC roof. It will not be connected with the masonry components. Then tiles are also to be avoided. So tiles should not be used wherever it is possible, but wherever it is required. In case of, again, unreinforced masonry walls, the tiles should not be pasted. In place of that, some sort of painting is recommended. Similarly, facade made of stone, ceramic, glass, etc., which can fall during earthquake, which can dislodge from the structure and fall during earthquake, that is restricted, that is prohibited. And any AEU which is there, or any AEU should not be nailed to unreinforced masonry infill, or it should not be connected or supported by unreinforced masonry infill. Similarly, any duct or piping as part of air conditioning or other services, that will not be anchored to the floor slab. Rather, it will be provided with a secondary framing system, and that framing system is to be connected with the primary framing system to beams, columns, and shear walls. So it will be connected using a framing. It will not be hanging from the slab. So these specific requirements are given in relation to hospital and critical buildings. So it is further explained in context of false ceilings. First of all, false ceiling will be used only sparingly, as I said, not commonly used in case of hospital buildings, and these will be attached to a secondary system. So, and that secondary system should not be connected to the slab above, but it should be connected to the beams or vertical RCC members. And no false ceiling shall be anchored to unreinforced masonry walls, as I said. And in case of when false ceilings are to be supported by false roof, for the roof, then an independent system is to be supported from the floor slab bottom. It should not hang from the roof, rather it should be supported above the bottom slab. So a support structure, a secondary frame is to be provided from the floor to the ceiling level. Then in case of glazing, also again it is to be avoided in hospital buildings as far as possible. Wherever it is to be provided, it will be designed in such a way, because glazing is being considered as a drift sensitive or displacement sensitive component. So it should be designed to absorb a lateral drift of R times delta. So R is the response reduction factor and delta is the drift at that level. So whatever story drift is occurring, if it is connected between two stories, so that much drift it should be able to sustain between the top and bottom level, and also from the sides. That much some mechanical arrangement we have to provide to absorb that much drift. So this mechanism which is holding the glazing, it should have the capacity to sustain out of plane vibrations also, because earthquake will have all the three components. So in plane displacement will be absorbed by this mechanism. At the same time, the out of plane acceleration is to be transferred to the structure. So it should be strong enough in out of plane direction. And what is important here and maybe interesting to you, that in case of all these glazing components, full scale experimental testing has been made mandatory. So it is not specified in the code whether it will be done on shake table or just the displacement, quasi-static or pseudo-dynamic displacement testing will be adequate. That is not mentioned, but full-scale experimental testing is required so that it can be ensured that it can absorb the in-plane displacement and it can support the glazing in out-of-plane direction, supporting or resisting the force, inertia force, which will occur due to out-of-plane acceleration. So that was about IS 13920 part 1. Let's now move to IS 13920 part 2, which is about buildings. And again, this also caters to different types of buildings. Not only RCC buildings, it caters to masonry, RCC, as well as the steel buildings. And the major changes which have occurred in this IS 13920 part 2 that I'm going to discuss. So part 1, this part 2 has first section which is related with all structures. That means when we say all structures here, we mean buildings of different types. So those provisions which are relevant to all types of buildings, those are included in section 1. Then section 2 is about masonry buildings. And the major change here is most of the provisions here are compilation of the previous code. So like whatever were there in IS 4326 regarding band and vertical reinforcement, those have been compiled here. And in 15988, whatever was available regarding confined masonry, those are also included here. Similarly, guidelines in 13827 and 13828, those are also included. And a table is provided where what type of masonry construction we can use in different zones. That is also given. So based on this guideline, we can decide what type of masonry constructions are suitable for different levels of seismicity. I will not talk about masonry buildings much. Actually, we will be talking about the additional criteria for concrete buildings. And one criteria which code has written in its scope, that the admissibility of different structural systems. Actually, this is specified in IS 1893, not in 13920. That's already given in 1893, and code is referring to that. And the code provides detailed provision now regarding planned density of structural walls. And those are varied based on earthquake zone and category of the building. And then similar criteria are also provided for steel buildings as part of this 13920 part 2. Now, regarding general provisions or scope, IS 13920 Part 2 specifies that cold form light gauge steel members shall not be used as part of earthquake load resisting system. So it is not saying that these are not part of scope of this code, so that the designer is free to use his or her judgment and background and skills to design such structures. It has prohibited use of cold form light gauge steel structures. So cold form light gauge steel structures, and this will have, as you can understand, this will have quite severe implications. So nowhere as part of lateral load resisting system, these cold form light gauge steel members can be used. What I can understand from the language of this clause, that you can use those as secondary systems or gravity load resisting systems, which are to be designed for the same deformability as the main system or primary system, but you can't use these as part of primary system. That's what is prohibited by the code. Then the provisions of this standard are applicable for all buildings and for especially for critical and lifeline structures, special structures, nuclear power structures. Additional requirements may be imposed by the associated authorities. So interestingly, it takes into account, it talks about nuclear power plant structures also. So nuclear power plant structures also will be governed by this code. In addition to that, there will be additional guidelines from the concerned authority regarding those structures. Dam, although it is not written here in this particular sentence, dam is not appearing, but there is a separate part on dam. Like part 2 is for buildings, there is a part on dams, which will come in due course of time. And what code says that in any case, whatever provisions are given in this code, those will be the minimum. So these authorities can enhance the provisions. Those can increase the minimum requirements of this code, but those cannot dilute below whatever provisions are given in this code. So those will act as minimum. Then the provisions for RCC buildings given in this part shall apply to monolithic RC construction. Again, this is very important, which have ductility to resist the effect of strong earthquake shaking. That means monolithic RCC construction we have to use. If we are using precast concrete components, then we have to demonstrate through full-scale testing. Again, full-scale testing is needed, that whatever precast system we are using, that has lateral stiffness, strength, and deformability capacities equivalent to monolithic RCC system. So it is not prohibited. The code is not saying that we can't use precast, but this condition is put, and this condition is quite stringent, and it is not only complex, it will be quite expensive also, because we have to do full-scale test to demonstrate that lateral stiffness, strength, and deformability of those systems. But in one way, it will be helpful that we can have some standard type of systems, precast systems, which can be verified for one prototype using full-scale testing, and then it can be used repeatedly. So that is allowed by the code. Then monolithically cast concrete structure shall be designed based on the results of structural analysis using a single three-dimensional mathematical model. So this has been underlined by the code now. Earlier also we were using 3D model only. Nobody nowadays was using any 2D model or hand calculations. In case of buildings were not possible. So those are quite cumbersome. So everybody was doing that, but now code has made it mandatory that there will be a 3D system. And in the model, moment continuity between beams and columns shall not be released. So whatever model, whether we are having gravity columns or we are having lateral load resisting columns, the release between beam and columns will not be provided. So whatever model we are making, the columns and beams will be monolithically connected physically as well as in model. So many times we were doing analysis where we were releasing the beams and columns. We were providing releases at the junction of beam and columns. That is not allowed by the code now. Then along one plan direction of the building, we can have moment resisting frame plus shear walls along one direction. So we can have different structural systems in different directions. In one direction, we can have a combination of shear walls and moment resisting frames, whereas in the other direction, we can have only moment resisting frames. And perhaps that is to be allowed by the code, because code is insisting that there should be minimum 10% difference in the time period of the structure in the two directions. So that difference generally can be achieved if we are providing shear walls in one direction and other direction we are providing only frames. So to achieve that, code has made it clear that it is admissible. We need not to provide shear walls in both the directions. In one direction we can have MRFs only. But there are other clauses. When we will look at those, then it may be contradictory. So there are some clauses, language is written in such a way where it can be contradictory. And maybe we can point out as part of the comments, we can point out that some of the clauses are contradictory. So this clause, which is saying that other direction we can use only RC MRFs, but RC MRFs are not allowed without shear walls in case of high seismicity zones. So there this may not be applicable. Then the planar MRF plus shear walls or only MRFs. The code is saying that these can be provided in such a way that these are designed for 100% of the effect of the design vertical loads and 100% of the effect of the total design earthquake load of the building. So that means these can be placed in the structure in such a way, and these can be stiffer than rest of the structures, so that these are attracting almost 100% of the load. And in that case, we can design these for 100%. And other members, we can design as gravity columns. So in other words, this clause is talking about provision for gravity columns. That means some of the members, some of the components we can have in our building which are not designed for earthquake force, which are designed primarily for gravity load. But later we will see, when we say gravity columns, those are not really designed for gravity alone. Those will be designed for the compatibility forces. So those will be deforming along with the structure. And due to that deformation, R times delta, whatever forces are occurring in those elements will be designed for those forces. So what does that mean? It actually means that those members should remain elastic under DBE. So when those are subjected to full DBE forces, R is equal to 1, those members should remain elastic. And how that will be possible? That will be possible only if the stiffness of those components under lateral load is much smaller than the stiffness of these members or these components which are being designed for 100% effect of the lateral load. So there has to be a large stiffness difference, because the lateral load will be distributed in proportion to stiffness. And those elements which are having much smaller stiffness will attract much less lateral force. And it may be possible to design those components to remain elastic under DBE. And such components we can call as gravity load components or gravity columns. It is not that any element, any column we can declare as the gravity column, and then we can decide not to design it for earthquake forces. So that will not work. Then the remaining planar frames which are not designed, those will be designed to resist the effects imposed on them due to vertical load and deformation compatibility, which I was talking. So all MRF plus SWS shear walls and moment resisting frames along each plane direction shall be selected to carry the design lateral loads only when moment resisting frames appear without shear walls. Okay, so what does that mean? That we can decide the moment resisting frames to behave as non-lateral load adjusting elements only if those are provided without shear walls in that plane. That means if the columns and shear walls are provided in the same plane, in the same frame, along the same bay, then we cannot treat those moment resisting frames as gravity frames. That's what is meant by this clause. And if those are different, if in one frame there are only columns, there is no shear wall, then we can design them without considering lateral loads. And in that case also, we have to keep in mind that the deformation compatibility is to be satisfied. So whatever forces will come due to deformation compatibility, it is to be designed for that. And when the design horizontal acceleration coefficient AH of the building is less than 0.05, then this provision may not apply. Meaning thereby that in that case, those columns which are in plane of shear wall, they can also be designed as gravity columns. Then it has been, although it was understood, but now the code has clarified that whatever design we are doing, we have to ensure these 5 properties from our design structure. One is the stability, that it should be stable under load. It should not topple or overturn as a whole. So that is the stability. Then it should have sufficient stiffness so that the interstory drift of the building is controlled. Then strength. So strength is actually controlling ductility. If we are providing ductility demand, if we are providing higher strength, the ductility demand will be less. Then the code also talks about deformability. Now, this deformability has been introduced, this term has been introduced, and it has not been defined adequately in the code. So it appears to be contradictory of the stiffness, because stiffness and deformability appear to be opposite. Deformability is the ease in deformation, or how much deformation the structure can undergo, whereas stiffness is reducing the deformation. So here we have to understand, there is a common understanding that if our structure is flexible, then its period will be longer, it will attract lesser force, and then its seismic performance will be better. Now, this is not true. Actually, a stiffer structure is required, especially when the structure is taller. Then we have to emphasize on stiffness. The interstory drift is to be controlled. So this concept that the structure, a flexible structure will perform better, it is applicable only to those structures which remain elastic. But we design almost all of our structures to undergo plastic deformation. So there, the flexible structures will not be performing better. Flexible structures will have large deformation demand. So stiffness has been given here, and this deformability, you should not confuse. Actually, what I have inferred from the use of the deformability term elsewhere in the same code, that they are talking about the capacity for inelastic deformation, that the structure should have such deformability that it can sustain those displacements which will occur during earthquake, provided with the stiffness. Now, another term is ductility. So ductility is the deformation capacity in plastic state after yielding. So after yielding, whatever deformation is occurring, so this stiffness, deformation, deformability, and ductility, these, and even strength, these are all interrelated. And a better or more clear definition of these terms need to be given by the code. Otherwise, this may be confusing. Although this is only at the level of philosophy, specific provisions are given later on, which we will be actually using in the actual design. So even if we are not very clear about what this deformability is, even then we can design our structures. But at philosophical level, this is causing some confusion that how it is related with respect to stiffness and ductility. That needs to be made clear by the code. So all the RCC buildings shall be designed and detailed as per this standard to resist earthquake hazard defined in, actually this is referring to IS 1893. So earthquake hazard will be defined by IS 1893, and this code will be, as I explained earlier also, this code will be designing and detailing RCC buildings. Now, this table I have taken from IS 1893 part 2. So it is not really part of 13920, but it has been referred again and again in 13920. So I have taken it. And what you see here, this is providing the admissible structural systems in different zones. So now you know there will be 5 zones, zone 2 to zone 6. So in revised IS 1893, there are 5 zones in place of 4. So a new zone, zone 6 has been introduced. So zone 2 to zone 6, these are 5 zones. And then different building categories, normal, important, and critical. So these 3 categories are also defined in IS 1893. So depending on the building category, that means the hazard involved with the building collapse and post-earthquake importance of the building, this category, which is reflected in its importance factor. So based on the importance factor and the zone, these types of structures which are admissible, those are given here. And here it is interesting to note, one system is given as DS. So DS is dual system. And then this is SMRF plus special shear wall. Now, I was also a bit confused that what is the difference? A dual system, how it is different from SMRF plus shear wall? And generally, in the previous code, we were thinking that only, that SMRF plus shear wall is the dual system. But the revised code is differentiating between the dual system and this system. And you can see in case of critical buildings, especially zone 4, 5, and 6, only dual system is allowed. Even SMRF with shear walls are also not allowed here. This is quite stringent. We have to follow, first of all, we have to understand what the code means by dual system, and this dual system is different than frame plus shear wall. Especially design frame and especially detailed shear wall, it is different than that. And in case of critical buildings, important buildings, it is not allowed. And other systems, another interesting thing you will find here, this FS1. So FS1 is representing flat slab. OMRF and SMRF and SSW, you are already familiar, so that you can understand. Only thing is this FS1 and FS2, 2 types of flat slabs. And you can see flat slabs cannot be used alone. Flat slabs are to be used with shear walls and frame. So everywhere you will see FS1 or FS2 will be occurring together with SMRF plus SSW. So both shear wall and frame are to be used along with flat slab. Flat slab will be used as secondary system, always along with some shear wall and some frame. Frame will be provided along the perimeter. So FS1 is that flat slab system which is having only shear wall and perimeter frame, whereas FS2 is having shear wall, perimeter frame, as well as intermediate columns. So in FS1, there will be only one bay of flat slab between the shear wall core or distributed shear wall and the perimeter frame. Whereas in case of FS2, multiple bays are possible. And you can see that FS2 is not allowed in 4, 5, 6. So the use of flat slab is limited in zone 4, 5, and 6. Even in 5, 5, and 6, even FS is not allowed. even FS1 is not allowed. FS1 is allowed in zone 4. So this is a new direction in our code. You might have observed this in case of IS 16700 also. So there is also a stringent limit about structural systems of buildings. What structural systems we can use in which zones and up to what height. Similar concept has now been introduced in case of low-rise buildings also, which are not governed by tall building code. Those buildings also, this concept has been introduced, and we should carefully look into it, because I'm not sure how much research has gone into it and how much it is based on judgment. So a collective judgment, judgment by the whole community, what type of issues we are going to get. So all those need to be brought to the code committee. So please look into it, and whatever comments you have, whatever comes to your mind, or whatever experience you have had in past, that experience will be very important. So please bring that into the knowledge of the code committee, so that if any change is needed in this, that can be taken care of in time. So to solve this issue of SMRF plus SSW versus dual system, I have looked into the code, again IS 1893 part 2, how it is defining. So it is defining special moment resisting frames with structural walls, which are designed as per IS 13920. So in any case, all our special moment frames and shear walls and dual systems are being designed for 13920. So that does not differentiate. Now, it again classifies this shear wall plus moment frame system as the one which is having well-distributed shear walls. So here the shear walls are well distributed, and the density, planned density of the shear walls is given like this. On the other hand, when it is talking about the dual systems, it is talking about special shear walls and special MRFs in the same principal plan direction in a single plane. That means within the same frame line, the shear wall and the frames are existing. So columns are in the plane of the shear wall. Then it is talking it as dual system. It is not clearly defined in the code, but from these provisions, I could make out that what the code is trying to say. It is trying to differentiate dual system from frame plus shear wall system. Dual system, it is calling those where the frame and shear walls are in the same plane, in the part of the same frame, planar frame. Whereas in case of frame and shear walls, the frames can be in separate plane. Some of the frames or some of the bays may have only beam column frame, and some of the bays can have only shear walls, or combination of shear wall and frame. So that is the difference. So in case of dual systems, the column should be part of the same frame. Then it will be qualified as dual system. And you can see from the table of response reduction factor given in IS 1893 that the response reduction factor provided for dual system is higher as compared to shear wall, special shear wall and special moment resisting frames. Then the limits, I come back to 13920 again. That part I have taken from IS 1893 because I thought that is relevant to understand the provisions of IS 13920 also. So coming back to IS 13920 part 2, there are clauses about beam cross section. So we were already having these clauses. Some changes are there. So the change is here regarding the detailing regarding the minimum reinforcement at different faces of a beam. So what the revised code says that at the bottom face of the beam framing into a column, at the face of the column, the reinforcement will be 75% of the steel on its top. Earlier this was 50%. So this will be 75% in beams that are part of the lateral load resisting system. That means those which we have not designed as gravity, we are designing those as lateral load resisting systems. So the reinforcement at the bottom face, we know at the bottom face the reinforcement comes out to be lower as compared to the top face, because at the top face the gravity moment and the earthquake moments are added together, whereas at the bottom face those are acting in opposite direction. One is hogging, other is sagging. So the reinforcement will not be less than 75% of the top. So this is a change. Whereas in other cases where the beams are not part of the lateral load resisting system, then we can go with the 50%. So there the limit is 50%. Even on those beams which are not part of lateral load resisting system, which we are designing as gravity system, there also there is a limit of 50%, which was there earlier. So that limit is applicable still. Now, in capacity design, calculation of design shear force is an important issue, and we have to calculate the shear capacity, and we have to compare it with the demand, and demand will come from capacity design as well as the applied force. So, and that demand, when we are calculating, earlier we were considering only the transverse steel. The concrete contribution of the concrete was not allowed in seismic conditions, and actually that has been taken from ACI 318, and ACI 318 explains in its commentary that during earthquake, due to cyclic loading, the concrete will crack and it will deteriorate. So it will not be, or the capacity of the section as a whole will deteriorate. And due to that, it was saying that if we ignore the contribution of concrete in shear, that will compensate for that deterioration in the shear capacity. Now, in the revised code, the code says that we can take contribution from the closed loops, we can take contribution from the ties, and we can also take contribution from uncracked concrete in the cross section. Now, this is a little bit complicated because we have to calculate that portion of the concrete which is in compression, and it is also not clear some portion of the concrete which will be compression for one direction of the earthquake will be in tension when the earthquake is reversing its direction. So whether the code means that uncracked section above neutral axis for that direction of the loading which we are considering, or overall, that is not clear. So this also needs to be, we can demand from the code more clarity on this part. Then, sorry, the demands which, or axial load demand, this is specifically in terms of axial load. So we know beams and columns are subjected to a combination of axial force and bending moment, especially columns. Beam, in case of beams, the axial force is mostly resisted by the slab, so the beams are mostly relieved from the axial force, but columns are subjected to axial force. So any member which is subjected to axial force, the axial force will be limited, because in presence of axial force, the ductility of that member, column in this case, will reduce. So RCC members are not ductile under axial compression. Those are also not ductile under shear. Those are ductile only under flexion. And when it is subjected to a combination of axial load and flexure, the ductility is reduced due to axial load. So axial load needs to be controlled. And that control is that in case of gravity load combinations, the maximum permitted axial load is up to balanced point. So the balanced failure axial load, where the bending moment is maximum, up to that point, we can allow under gravity load combination. And in case of earthquake load combinations, those combinations in which earthquake load is also appearing, the stress over the cross section should not be more than 0.4 FCK. So stress, compressive stress due to axial load is reduced to 0.4 FCK. And this is on gross section, although code has not clarified this, but the provision, this provision was there earlier also, and it is available in other codes. So it refers to 0.4 FCK on gross section. Then this clause was earlier also, that the beam should be, the column should be stronger than the beam, and the ratio of the column strength to beam strength should be more than 1.4. Now this has been further elaborated. So earlier it was just given that summation of moment capacity of the column should be more than the summation of moment capacity of the beams into 1.4. So this has been further explained. 4 combinations are possible. So the code is clarifying that this check is to be made in the 2 directions separately. So in X direction, we will consider 2 cases when the earthquake is considered in minus X direction and earthquake is considered in plus X direction. And MUC is representing the capacity of the column, and MUB is representing the capacity of beam, and H is representing hogging, and S is representing sagging. So when we will be considering the summation of the moment capacity, one beam will be in hogging, another beam will be in sagging due to one direction of earthquake. And similarly, we will calculate the moment capacity of the top column and the bottom column. And it will be at the top of the bottom column. Okay, and here it is bottom of the top column. So top column's bottom and bottom column's top. So that is clarified. So it is the same provision. Only thing is that the code has clarified. And in case of column, there is another issue that when we are calculating the moment capacity depends upon the axial load. So which axial load we should consider while calculating this capacity. So that is also clarified by the code, that we have to calculate the nominal bending moment capacity corresponding to the factored axial load for shaking in that direction. So when we are calculating this in X minus direction, then whatever is the factored axial force under the load combination in that direction, that axial force we will consider. So some of the columns due to earthquake will have additional compressive force. Some of the columns will be relieved of compressive force because due to earthquake there will be tensile force. So we will consider both the conditions. So for example, the compression due to earthquake is coming, let us say, in X minus direction. So tension will come into picture in X plus direction. So all the columns will be checked for both the directions when we will be using these 4 combinations. Actually, software like ETABS is already doing that. So that is already there. Code has clarified. Then in case of structural walls, most of the provisions regarding the minimum dimensions are same, which were earlier there. What I found interesting and new was this, that the minimum thickness 300 millimeter, that was for coupled structural walls. Earlier also it was 300 meter for coupled structural walls. What has been added is that the buildings with beams framing into wall in the direction perpendicular to the minor axis. Now the language is a little bit complex. You try to understand the direction perpendicular to the minor axis. What does that mean? What is the minor axis? So minor axis is the one which is in the plane of the shear wall. So the horizontal direction in the plane of the shear wall. In other words, it means that if a beam is connected to the shear wall perpendicular to it, then the thickness should not be less than 300 millimeters. That's what it is trying to say. And it should not also be, the previous clause is saying that it should not be less than 20 times dB. So that clause was already there. So same has been reproduced. Then only if the bending, this clause is related, this confusion was there, and I have in some of my talks earlier with Epicons, through Epicons platform also, I have discussed this issue. There was a lot of confusion regarding what is a column and what is a shear wall. When we can design a column as a shear wall. and I have presented this in the code committee also, that actually it will not depend upon the size of the cross section. It will depend on the shape of the bending moment diagram. So I have shown earlier, I could not copy that, otherwise it would have been good if I have copied that slide now also. So in case of a shear wall, the bending moment is not changing its sign within a story. For example, in case of a column, the bending moment at the top and bottom is causing curvature in opposite direction. Tension is on different faces. So a frame member, that is a column member, vertical column member, will bend in double curvature. Means the moment, the sign of the moment at top and bottom will be different, and there will be a point of contraflexion in the middle. So what the code says, that shear wall is that element, that vertical element, which is having a single curvature along the full height of the building. So this is okay. This matches with what we had discussed earlier, that shear wall will try to. But there is one difference here. Sometimes when we are having shear walls coupled with frames, we have dual system, then it is possible that the direction of the bending moment may change at one point. So there can be one point of contraflexure within the shear wall where the bending moment is changing direction along this height. So this statement needs to be clarified, that in that case, it will not behave like a column. Still, it is a shear wall. So in shear wall also, one change is possible. The difference is that in case of a column, every story is having a point of contraflexion. In case of shear wall, the whole shear wall will have maximum one point of contraflexion. If shear wall is used alone, that means the building is having only shear walls, then those will deform in the same pattern, and there the point of contraflexion will not be there. Those will deform in single curvature. But if we have a mix of frame and shear wall, this phenomena is known as frame shear wall interaction. Due to frame shear wall interaction, it is possible that shear wall may have a point of contraflexure in the in some upper story level. So that will also remain shear wall. That we have to understand. So that perhaps code has to make a clarification. And interestingly, code has gone one step further, and that has made a bit complexity. The code says that above check on bending moment diagram in vertical direction should be made owing to earthquake shaking along both the direction of the shear wall, short and long dimensions in the plane, in the plan. Now that means we have to check the bending moment diagram in plane direction as well as out of plane direction. But in out of plane direction, depending upon the out of plane stiffness of the diaphragm or whether any beam is connected or not, the shear wall can have a point of contraflexion in story. It may, in out of plane, it is not as stiff as in plane. So out of plane, it may bend in double curvature. So I'm not sure whether this is intended by the code, that in out of plane also we have to make checks, or this means something else. Perhaps code wants to say something else. So this also needs to be brought to the notice of the code committee, that they should discuss on this, that they really want that in out of plane direction also the shear wall should bend in single curvature. Otherwise, it will be treated as column. But one thing is sure from here, although it is not explicitly written in the code, that the shear walls will also be designed for biaxial moments. So generally, we are designing shear walls for in-plane moments only. We ignore out-of-plane moments. But with this, it is intended, although it is not explicit from here, it is intended, and ACI 318 is explicit. ACI 318 says very clear that the shear walls should also be designed similar to columns, in considering the moment in both the directions. Now, then what is the difference between the shear wall and the column? The difference is in the ductile detailing. So in case of column, the plastic hinges can form at top and bottom of each story. So we have to provide a special confining reinforcement near the top and near the bottom. Whereas in case of shear wall, the plastic hinge will form in the bottom portion. So we are providing special confining reinforcement near the bottom portion, and that too along the edges, boundary of the shear wall, because near the boundary the concrete will be subjected to higher strain as compared to that near the neutral axis. So only that portion of the concrete which will be subjected to higher strain, that needs to be confined. So in case of a shear wall, we are confining only the boundaries. So confinement is provided generally within the boundaries, and middle portion is not provided with special confining reinforcement. So that's the only difference. Otherwise, the principle of design remains the same. Similar P, MX, MY interaction curves, interaction surfaces are to be developed for shear walls also, for designing at any section. Now, the capacity design concept has been extended to shear walls. So this was earlier missing in our code. So it has been extended, and it has been mentioned now that the shear walls will also be designed for shear capacity, and that shear capacity will be obtained from 1.4 times the design moment capacity. So whatever design we have done, we will calculate that nominal capacity, and 1.4 times, as we have done in case of columns and beams, 1.4 times of that we will use for designing of shear walls. So in case of shear walls, particularly the capacity design, we are still inadequate. So if we look into the provisions given in ACI 318, more clauses are needed, because it is not just calculating the shear force at the base, the distribution of the shear force along the height, that is also important. So that part is still not given by our code. For that, we will have to refer ACI 318 yet. So we can point out this also, that the distribution of the shear along the height should also be proposed by the code, so that not only the shear reinforcement at the bottom can be checked, shear reinforcement and even vertical reinforcement at any level along the height, that also needs to be checked. Then similar clause as was there in case of columns on axial load ratio has been provided for shear walls also, that the shear walls under vertical load combination, that is gravity load combinations, those should have axial force within balance point, and when those are subjected to earthquake loads, or rather when we are designing for earthquake load combinations. So every shear wall will be designed for earthquake load, but in the combinations in which earthquake load is not there, we can allow up to balance failure, and when earthquake is there, we will allow up to 0.4 FCK. Then this is quite useful. Earlier, our code was not clear about the length of the boundary elements. What portion of the shear wall should be confined as boundary elements? So that has been now included. Although it is simplified, it is simplistic, but still some guideline is there that the length of the boundary element will be 2 times the thickness of the web, or 0.15 times the length of the wall, 15% of the wall on each side, or minimum 500 millimeter. So minimum 500 millimeter length will be confined as boundary elements. Then the confinement reinforcement will be same. Design of these is similar. Only thing is one clause on spacing has been included in this revised code, that is 100 millimeter, but may not exceed may be relaxed to 150 millimeter if maximum distance between cross ties and parallel legs of the link is limited to 200. So if we are limiting the horizontal spacing between the ties, the vertical spacing can be increased up to 150 millimeter. But interestingly here, the code says 100 millimeter, and then it says need not be less than 100 millimeter. So this is not very clear. Language is not very clear. Perhaps this 100 millimeter, it is saying, I don't know. It can't be related with this 150. It can't be related with this 100 millimeter also, because in that case it will be in 100 millimeter only. In any case, it will be 100 millimeter. because it can't be more than 100 millimeter. It need not to be less than 100 millimeter. So some issue is there in here in the language. So that we need to find out. The code committee has to look at it. Now, further useful guideline is given here. When a beam is framing into the minor axis of the wall, then the boundary element shall be provided at that location. So this issue also we have discussed, that when a beam is connected to the shear wall in out of plane direction, then wherever it is connecting, there also we have to provide a boundary element, and this will be provided for the full length of the wall. And the design of such a boundary element shall meet the requirements of minimum column dimension. So whatever minimum column dimensions clause is already existing, actually there is no change in that. So minimum dimension 300 millimeters. So that will be satisfied by this boundary element also. And the minimum column to beam strength ratio 1.4, that also will be ensured when the beam is framing into the shear wall in out of plane direction. Similarly, in case of coupling beams, now two types of coupling beams have been classified: flexure controlled and shear controlled, depending on the span to depth ratio. So if a span to depth ratio is less than 5, it is called shear controlled. If span to depth ratio is greater than 5, then it is flexure controlled. And different governing criteria for flexure controlled and shear controlled beams is given. If it is flexure controlled, then it will be designed as per normal beam criteria. So whatever normal beams we are designing, if it is greater than 5, whatever capacity design is to be performed, that will be performed. If it is shear controlled, then we have to design it with diagonal reinforcement. The diagonal reinforcement provision is same as it was there in the earlier code. So I'm not going into that detail. But what has been specified here is that the shear stress is more than this, but it has to be less than tau c max. So in no case the shear stress in coupling beam, even when it is provided with diagonal reinforcement, can be more than tau c max. And the expression for tau c max has been taken from revised, or rather under revision, IS 456. You may be knowing that IS 456 is also under revision, although the code has not come. I have not seen the draft code. I don't know whether it is still in wide circulation or not. At least I have not come across that copy, but some information I have got from the people who are there in code committee that there are revision, and specifically the shear capacity clause is being revised significantly. And that portion of IS 456 has been reproduced in IS 1893 part 2 or part 1, I do not remember. I think part 2, it has been reproduced. So that is also there. And this has been taken from that only. So tau c max can be calculated like this, but here they have taken this strength as actually it is square root of C case. They have taken 5 MPa. So they have taken constant. So 5 MPa delta. So tau c max will be calculated using this formula. Suppose we assume that there is no axial force, so this will be 5 MPa. So the shear stress cannot be more than 5 MPa irrespective of the grade of the form. So that is the final implication of this clause. And if in any case the shear stress is exceeding tau c max, this value, in that case the code is saying that you have to redesign the coupling beam to bring the shear stress within tau c max. Now how you can do that, how you can redesign? For that you have to actually reduce the depth of the coupling. So you can't redesign it by increasing the depth, because if you are going to increase the depth, the moment capacity and hence the capacity shear is going to increase. So shear demand will go on increasing if you are increasing the depth. So please keep in mind, you can achieve this design only when you are reducing the depth. So when you will reduce the depth, you can redesign it. Then some clauses about mechanical couplers and splices are there. What I found interesting is this, although it was intended earlier also, but now it has been very explicitly written that welding is not permitted in any earthquake zone. So any type of welding between longitudinal bars, between transverse bar, between longitudinal and transverse bars, no welding is permitted. So that is made clear by them. Then there are some clauses which clarify regarding the design and analysis. So regarding the design, it has been clarified that special moment adjusting frames may be used in any earthquake zone except in building taller than 15 meters. Now, this is somewhat contradictory to what the table I have shown in IS 1893, because there it shows that in zone 5 or 6, a special moment frame alone cannot be used, whereas it is saying that up to 15 meter we can use that. So this harmony between the two codes needs to be ensured. These should not talk contradictory provisions. So that I wanted to highlight here. And then in analysis, when two moment frames, this is again a very interesting thing, very interesting provision, which is going to modify how we are configuring our buildings. So when two moment frames oriented in orthogonal directions intersect, the possibility of beam yielding in both orthogonal directions simultaneously shall be considered. And it is preferable to plan buildings to have independent planar lateral load resisting moment frames in each direction. Now, what does that mean? It doesn't mean that the frames which are non-orthogonal, or in other words, it wants to clarify that the orthogonal frames are not independent. So what are these independent frames? Like the perimeter frames. So there are no common columns between the two frames. So those type of frames are preferable. That's what this clause is trying to say. That means all the lateral load resisting system we can put at the perimeter, and intermediate frames can be gravity frames, something like that it is intended. And in our conventional grid frame system, where we are having beams running in both the directions at some interval, so in grid frames we have to consider yielding in both the directions. Actually we do that. So we have to consider when we are designing the column, we have to consider the biaxial moment capacity. So we will assume that the column will yield, the beams in one x direction will also yield, beams in y direction will also yield. Although I'm not sure whether code is exactly meaning that, because in that case, the demand, the moment demand on the column will be very high, because it will be subjected to the capacity moment in x direction as well as y direction simultaneously. Whereas in real earthquake, when we are getting maximum moment, which it may cause yielding of our column in one direction, the other force is 30%. So whether the column will yield under 30% of other direction beam or not, that is not very clear. So this also needs some discussion and some careful looking upon from our side. Then in case of design, the code also clarifies that special moment resisting frames with special structural walls designed as per provisions of IS 13920, those can provide adequate inelastic deformation. And yielding of beam column and beam wall joints in special moment resisting frames with special structural walls is not permitted by this standard. So yielding is not allowed. Now it is not very clear how that will be ensured. Perhaps it is intended that if we follow the detailing for the joint, which is already there in our code regarding the provision of stirrups in the joint, 50% in case of confined joints, and 100% in case of unconfined joint, and then checking the joint in joint shear. Those clauses are already there. So perhaps we follow those. This clause will be deemed to be satisfied. But the code is specifying this without specifically mentioning that how it will be ensured, how in design it will be checked. Then it is preferable to plan buildings to have independent planner. This is something similar to what I was discussing earlier. So we have to plan. Okay, this is related to shear walls. The previous one was related to beam column frame. So similar provisions are there for shear wall also, that independent planar elements in the two directions should be used, and fractional yielding of beams supported on weaker axis of the structural wall is not permitted. Now this is not clear. What does that mean? That means the beam will be designed stronger than the shear wall in outer plane. It is, and it is saying not permitted, not that it should not be it should not occur. It's saying it is not permitted. It is very rigid. That beam supported on weaker axis means out of plane beams. So those beams which are connected out of plane direction in the shear wall, so those will be designed to remain elastic. Perhaps code means that. So that appears to be a stringent criteria which we need to consider. Then, as I said, I was also a bit confused about dual system. So there are some criteria for dual system also given. So here also it is mentioned that along any one plane direction, at least two planes of dual system should be provided. So here it refers to as planes of dual system. So planes of dual system means that in the same frame, along the same line, we are having shear wall as well as moment column frame. Then we are calling that as the dual system. So these were the points which I thought are interesting and are different from the previous code. There may be some other interesting points also, which may be of interest to you, but those were available, those were already existing in the previous code. I have not discussed those. So I will stop here, and we can now take up the questions. Maybe those which were compiled before this, or maybe those which we have, which our
We'll take
audience has read
we'll
now.
take both. We'll first do the received earlier.
Okay.
We can take the questions by Mr. Bhukani. I'll try to. Yeah, well,
Yeah, sir. Arvind ji, I have shared the screen.
Yeah, you already shared the screen. Yeah.
I think that there are 3 points that.
You can continue.
Yeah. So this was a much needed clause in RC shear walls, that the capacity based design be followed. However, the thing is that this particular codal provision, where those estimated as 1.4 times the design moment capacity estimated as per 13.3.2.2, is not a very clear statement according to me, and it might lead to ambiguity in a design office. I'm talking in terms of a design office. So maybe if we can have something like the shear capacity required to be developed in the structural wall to achieve 1.4 times the design moment capacity for all load combinations involving earthquake loads, or in the ACI 318 format, where the shear force demand estimated from all load combinations including earthquake loads multiplied by the ratio 1.5 times the design moment capacity to the moment demand MU.
Right.
So I think this will be easier to follow in a design office.
I fully agree, because there is no direct relationship between shear wall and moment. So if you know the moment capacity of the shear wall, you can't calculate shear force directly.
Right.
So there is no length available or equivalent height available that you multiply shear by that equivalent height, you will get moment and vice versa. So the relationship between shear force and bending moment as in that system, and that is reflected by the ratio of the shear force and bending moment when we have performed analysis for different load combinations. So that is clear from the suggested language. So I think we can definitely propose this to the code committee, because this is a serious issue.
The
And
other
I will suggest that in addition to that, we should also suggest that the distribution of the shear force and bending moment along the height, the shear force envelope and bending moment envelope should also be provided by the, because it is
at all,
not the design only at the base. We have to
yeah,
design
at
along
all
the height
floors,
also,
at all floor levels.
at all floors. Yes.
Right, right. Secondly, so we had done this exercise in our office where we were finding out the length, boundary zone length, based on the end zone length, based on the neutral axis depth as per the ACI 318 or the Eurocode.
Okay.
And we are finding that 500 mm or 0.15 LW is, even when the load is at the balance point or maybe around the balance point, that will be much smaller than what is required
Okay.
as per these codes. And we
Okay.
have a very nice formula in our IS 13920, which gives the XU by LW. So if we can calibrate the end zone length based on the XU by LW, it's a simple formula. It's just a one-step calculation in Excel. So if we can, maybe give a recommendation regarding the end zone length dependent on the XU by LW. So that the
Yeah.
force aspect is completely removed and the capacity aspect of the end zone remains.
Okay.
So I think no, the reason I'm stating this is that there are a lot of times that two different practices, two different offices will produce very varied end zone lengths depending on their philosophy, and they
Yes.
can vary 2 times, 2.5 times, 3 times also. So I think some rationalization there, if you can suggest to the codal provision, that would be great. And a lot of times this diagonal reinforcement, um, from the analysis, we are getting an MU and a VU. But in our code, we are just giving the diagonal reinforcement based on the VU. But a lot of times in analysis, what happens is that the diagonal reinforcement is governed by ASD, even though it is by moment, even though it is shear controlled beam. Like the horizontal component divided by the lever arm will give a lower moment capacity than what is obtained from the analysis.
I was under a different notion here. I was thinking that both should be give me the same, because the equilibrium is to be satisfied. And when we are satisfying the equilibrium, the relationship between shear force and bending moment, that
Is
is
the
also
same.
governed by the geometry. And this force component of the diagonal, that is also governed by the geometry. I was thinking, although I have not done any exercise, I was thinking that you calculate either way, it should come out to be the same area, whether you are calculating using shear force or you are calculating using bending moment. So I don't know whether if you have checked that. In some cases, practically you
Sir,
have
we
checked
have
that
done at least a lot of buildings, because we have our spreadsheet calculation where
okay.
we calculate the ASD based on the shear and the ASD based on the AVD based on the moment. And generally, a lot of times, especially in the range of L by D is approximately 2, we are getting that the AVD is governed by the moment. I don't know the reason why
So
analysis gives.
please share some of the
Yeah,
calculations.
yeah. So if
We
we
can
can,
look at that.
right, sir. We'll do that. So maybe a formula for a moment also, so that we remain on the safer side.
Yeah, and I was under this impression that both should come out to be the same, because there is a
Okay.
relationship between Mn and Vu,
Right.
and that also comes from the span L by 2,
Right.
and this will also come from that L by 2.
Right.
So
Sir,
I'm
I'll
not.
share you certain
Yeah.
calculations so
Let's
that
look at some real calculations. Then we can understand better.
And one more question I had, mainly with respect to the links. The links, the ductile links, we say that we should limit the FY to 415. I mean, we understand that for shear, and a lot of codes allow around the world, for the calculation of ductile, they go up to even 700 MPa. So is there a
Yeah.
reason? within our code where
Region was simple. That the old code was based upon experimental results, in which only up to that level it was tested. But now actually that is part of IS 456, not 13920. So in IS 456 changes are being made, and that issue will be taken care of. So I have heard from one of the committee members
Right.
from IS 456 that they are taking that into account.
Okay, sir. Okay, sir. These are the questions from my side.
Okay, perfect. Questions as well as suggestions. That's what we want.
Right, sir. Thanks a lot, sir.
Thank you.
Thanks.
So Parlekar sir, we can take further
Yeah,
questions.
we can take the questions, I think, from participants first, because
Yeah.
they are present there. We don't
Right.
know.
Written questions we can give
Yeah.
answer also in writing if required.
Correct.
I think they will be more curious to know.
Yeah.
answer.
Questions will be raised by me also, as well as Hemant. I'll request Hemant also to study something and take the questions, maybe 4 or 5 questions each. So we'll take right from start. Intention of code is very clear in proposed draft code. However, clause numbering in the entire code seems to be improper and confusing. So that is a general comment. We can't comment on that. Next question is, in the new code IS 13920 applicable to zone 3 and above, optional for zone 2 is removed. Is the new code intended to exempt the 13920 in all zones if designer wish to do? Is it that?
Okay. So when you say code is exempted, actually you mean that special tactile detailing is omitted. So now code has given guidance for all the zones. But if you look at that table which I was showing, in case of zone 2, OMRF is allowed. So it is the same thing. So code is not saying that code is not applicable to zone 2. In zone 2, we need not to do SMR. That's the approach.
One related question is in my mind also, how this whatever system given by 1893, are they independent of height?
So yes, these are independent of the height, but when the height is increasing more than 150 meters, no, not 150, 50 meters,
That is, it
then
will cover by high rate.
16700 will come into it.
That is okay, but what about
these
lower
ductile
heights?
detailing clauses are irrespective of the building.
I'm not talking about ductile detailing clauses. The clauses related to which systems are permitted.
Yes, those are, I mean, as you have seen, but there is a contradiction. In one clause, it was written 15 meter. We can allow SMRF up to 15 meter. Whereas in that table, in IS 1893 table, there is no mention of height. So it is applicable to all heights.
Next is IS 1682023 will be superseded by this code. Which is this
Yes,
code?
so those other codes, those will become part of it. So those will be withdrawn when this code will come.
One practical question is, in 3D analysis, if an FAM error due to plate modeling is there, then modeling in parts will help to reduce the error. In that case, how to proceed with 3D model as in the code? It is saying that it has to have one single 3D model.
Yeah, that I understand that we whenever, I mean, those who are doing finite modeling, they are aware that there are many possibilities of errors in the model. So many a times we can get not wrong, sometimes even absurd results.
Yeah.
So we have to check our model, and those types of checks where we are first doing in parts and we are doing some manual checks. So those are needed. So those we have to do. But final design has to be based on 3D. That's what the code is saying.
Next is, for what load combinations the deep beam has to be designed for diagonal reinforcement?
Or what load factor?
Load combinations.
Load combination. I mean, all the load combinations. There is no separate load combination. So those load combinations which we are using for design of shear walls and frame, same load combinations.
Yeah, Hemant, can you take further? Is there Hemant is there? All right. Yeah, I'll just continue for 1 or 2 questions.
There's somebody asking, yeah, can you hear me?
Yeah.
In shear wall to check point for contra fracture, shall we need to check for equivalent static force as in case of the response spectrum, it is difficult to get this negative value.
Yeah, it's correct, but from the shape we can get. So if you plot the bending moment diagram, so what will happen in case of columns, it will not be point of contraflexion, but we will get a point where in the middle of the column where the bending moment is reducing, it is becoming 0, and then it is again increasing. So from the bending moment diagram shape we can identify. But if there is any, I mean, you are right. If there is any confusion, if you can't decide, then we can do static analysis, equivalent static load analysis, and see how the structure is actually behaving.
Because the point is the sign is lost in this response
Yeah,
spectrum.
sign is lost. So rather than getting point of contraflexure, I mean that two triangles, we get the triangles on the same side.
Then the next question is, in case of shear walls of size around 2 meters by 0.4 meter, which are bending in the single curvature along the major deflection, but has double curvature along the minor direction due to the beam framing along the minor direction, can we provide the BE, or we need to treat it as column and provide confinement along the whole length of the wall in the weaker direction?
Yeah, I mean, that's the question which I was discussing, because when code is saying that we have to consider this bending moment in both the directions. So we can provide confining reinforcement at the bottom only if the maximum bending moment, or DCR, demand to capacity ratio, can exceed 1 at the bottom. If there is a possibility of plastic hinges forming at other locations also, we have to provide confining reinforcement there. So if there is a possibility of plastic hinge formation, that means that the bending moment is changing sign. Maximum bending moment is occurring at top and bottom in out of plane direction also. We have to provide ductile detailing, because as far as the vertical reinforcement and section is concerned, it doesn't matter. It is same for shear wall and column. The difference is in the detailing, confinement. So in that case, the confinement is to be provided like a column in out of plane direction, both at top and bottom.
One similar question is on my mind also. Since when the lateral load wasting systems we are defining, can any such shear wall can be considered as a gravity column in other direction?
Gravity column cannot be considered in one direction.
Yeah, that's what. so because they are saying that
what we can ensure is, I mean, we can see that, I mean, perhaps what I'm understanding from your question is that suppose yielding is not occurring in one direction moment, yielding is occurring in plane.
In plane,
and initially shear walls were supposed to be so. Shear walls were just
in plane, correct? Yeah.
In plane, out of plane, those were not attracting. But then we started connecting by beams in out of plane also.
Correct.
So if these are connected in out of plane, then there are all the complications. So the key is, the key to understand the behavior is that if there is a possibility to form hinge, we have to provide ductile detailing. If somehow by any means using gravity design or whatever, if we can ensure that under DVE it is not going to yield, it will remain elastic.
If there is no, if there is no frame in other direction, then whether it can be done.
If there is no frame, then out of plane bending moment in any case will be very small, and in
very
that case,
small, correct? Yeah,
very small, and the shape will also be different. So we will not get point of contraflexure in the middle. Then it will be, then it will classify for that definition of shear.
Yeah, Hemant.
Yeah, the next question someone is asking, why 0.4 FCK check have been given for the shear walls? Does code want to give more SPD of walls in both the directions, as if walls are passed in 0.4 FCK, when mostly walls will be having minimum percentage of steel of 0.25%?
Actually, the problem is in presence of axial force, ductility reduces. So we can permit some axial force on those members which are yielding, and shear walls are yielding. Columns we can even save against yielding. So in case of column, we can design column stronger than the beam, and it may be possible, although it it is difficult. It may be possible theoretically that column we may not allow to yield. But in case of shear wall, that is not possible. Shear wall has to yield at the base. We are designing it in such a way. So in that case, it is important to control the axial force. If we will allow too much axial force, if too much axial force is coming on the shear wall, its ductility will be compromised. So that's why the 0.4 FCK is important in case of shear walls.
Okay, similar question to that again, whether we should need to consider only axial load only for calculation of 0.4 FCK check, or axial plus flexure stress need to be checked in the seismic combination.
So axial force will be first used to check the limit. It should be less than 0.4 FCK. If it is more than 0.4 FCK, we have to change the configuration. Then whatever axial force is coming, which will be less than 0.4 FCK, that will be considered in design using P-M1-M2 interaction, P-MX-My interaction. So both the moments and axial force we will use in design, like we do in case of columns.
Okay. Next question is for beams with L by D equal to 4 to 5, how diagonal reinforcement can be detailed
Yes.
at the boundary, means the limit of 5.
Yeah, up to 5 it is allowed.
So he's asking how the diagonal reinforcement can be detailed in that L by D equal to 5.
Oh, detailed. Okay. What he means is that the angle will
Angle will be very flat. Yeah.
Yeah, that's true. So we have to calculate. In that case, we have to provide higher reinforcement.
You can provide some haunches for that. Yeah. Sometimes end haunches, so to accommodate the diagonal reinforcement.
If you are providing haunches, then L by D will be modified.
Yes.
Yeah, that's true.
So then L by D will reduce. Fine. I mean,
Haunches, local haunches. I'm talking about local haunches.
It should accommodate higher angle of the reinforcement.
Yeah, that only for detailing purpose.
Yeah. So somehow the angle of the diagonal is to be increased.
Similar question on the same lines again. Someone is again asking for the beams with L by D less than 5 shall be treated as a shear controlled coupling beam. However, for beams with L by D equal to 4 or 4.5, angle of diagonal reinforcement will be very less, approximately 10 degrees. So whether it is actually effective, as per ACI, for such action, minimum 25-degree angle is recommended. So can you throw some light on it?
Yeah, so that is the problem with our current code. We can raise this in our comments.
Yeah,
to the code committee.
Right. Then someone is asking maximum shear capacity, tau C max is given as 5 as per the new draft. But in case of shear wall for wind design, as per IS 456, tau C max is 0.17 FCK. Mean to say if M70 grade of concrete is used, the wind combination will have the limit of 11.9. But for RFA, it is only 5. So how this may difference is allowed in both the lateral load combinations?
Yeah, I'm not aware. Please excuse me. I'm not aware what is the source of this 5 MPa. Why this 5 MPa is taken in case of earthquake. Although it may be different, that we can understand it can be different in wind and earthquake. But I'm really not able to explain why 5 MPa has been taken. So this again we can raise to the code that this 5 MPa, even in case of high strength concrete, and nowadays we are using stronger concrete. So code committee can recheck that whether this 5 MPa is due to some other region or how this is appearing. So I really cannot answer that because I'm not aware how this 5 MPa has come.
Okay. The next question is for diagonal reinforcement. Reinforcement is to be embedded for 1.5 times LD in case if the length of the wall doesn't permit to have 1.5 LD as along the diagonal, can be bent into the wall.
Yes, we can bend into the wall. In fact, bending into the wall will be more effective.
Okay. Next question is how independent planar systems are possible in practice. Though I give 2 columns for each direction, slab will be connected to both directions. That means transfer of the force will be there.
Sorry, I could not hear the first
I think
statement.
your question is also not clear. I will read again. How independent planar systems are possible in practice?
Independent planar systems are possible.
Yeah.
Okay, okay. Yeah. So I was having some example. Actually, in ACI 318, or I have taken that from Mohile's book. That is in one of my presentations. So the whole frame need not to be lateral load adjusting frame. Part of it. So corner column may not be part of lateral load adjusting element. That's what is shown in that figure. So it is possible to have independent lateral load adjusting systems. So for example, if I'm considering a perimeter frame, the corner columns will not be part of the lateral load adjusting systems. Those will be considered as gravity.
Then how do you detail that? Means it is strictly connected. No?
Means the size of the
Size,
interior
okay.
columns will be much larger as compared to the corner. So exterior column will take much less load. And if it is taking much less load, we can design that to remain elastic.
Okay. The next is in case of sway, shear calculation for flexible beams, especially in tall buildings. Beams in flexure are designed for wind and moment of resistance of beam will be from the wind combination. But in earthquake, there will not be much moment. Then also sway shear to be calculated from the wind combination moment or not.
Sorry, it's not clear. Sway shear, what is meant by sway
See,
shear?
in
Actually,
case of
this,
sway,
these shears
sway
to be
shear.
calculated by moment capacities, not by forces. No?
So is question regarding capacity shear design of beam?
Capacity shear design. I think there is some confusion.
Okay. So
These
that-
shears are calculated by capacities, not
Right. The actually provided reinforcement and cross section we have to use, not what is we are getting as getting from the analysis from earthquake forces. Actually provided capacity.
I think if I can comment, I think the entire code is not based on analysis, but the capacity of whatever
Right.
is provided, right?
Yeah.
Not entire code, we can't say that because the sizes will be governed by the applied load only. Na?
Yeah,
And
but
then the provided capacity is only deciding hierarchy. So there are two issues. One issue is that for how much load we are designing the building, and then what is the hierarchy within the those elements. So hierarchy will come from the provided capacity.
Okay.
I think this is another common question that is always asked for the structures where the wind loads are governing over the seismic loads. Detailing of the structure is still to be based on the seismic force only.
True. The reason is that when you are saying that wind load is governing, wind load, we are comparing wind load with reduced earthquake force. And reduced earthquake force or that reduction in earthquake force comes from ductile detailing only. So if you can show that wind force is governing or wind force is higher, even when I take R is equal to 1 in earthquake forces, then ductile detailing is not needed. But if I am using R to calculate earthquake forces, means I'm using or I'm taking advantage of ductile detailing. So I have to provide ductile detailing in that case.
Okay, the next question is whether horizontal bars are to be kept at the slab and wall junctions also. Vertical bars are, I think, continuing to the next floor. I don't get it. What exactly means to say?
So perhaps he means that the continuity of horizontal reinforcement and vertical reinforcement at junction of slab and wall.
Wall,
Yes.
yeah.
So horizontal bars will also be continuous, vertical bars will also be continuous.
Okay. What is upper limit of the shear stress as per the code when you have coupling beams with diagonal reinforcement, as the transfer shear is via axial force to the diagonals?
So just now we discussed in response to one question also the tau C max.
Yeah,
And
by
the
five-
tau C
5
max is
MPa.
coming from 5.
Yeah.
So 5 into delta. So that is the maximum stress currently what we see.
Somebody asking, can we use steel plates to accommodate for the additional shear when it exceeds that which can be provided by the stirrups?
This issue we discussed in much detail in one of our talks, one of our lectures. We can use steel sections. I will say steel sections, not steel plate. The problem is that whatever steel section we are using, that needs to be designed for anchorage into the shear walls, for bearing stress. So if we are using steel plates, it will be difficult to design under the bearing, because the area, contact area, which is transferring moment from the steel plate to the shear wall, that contact area will be very small. So it may not be possible for steel plates to satisfy that. So I will suggest use a steel section in place of a steel plate, and then design that for anchorage. Procedure for design of that anchorage is still not available in any code, but it is available in research papers, and I have also shared. So if anybody is interested in that, please write an email to me. I will share that presentation and that paper.
Next question is there any information on publishing of codes for seismic evaluation and strengthening of existing buildings in the light of the new code changes?
Yes, the information available with me is that it is in process. But when that process will be completed, sorry, I can't say, but it is in process. It is being done.
How do we arrive at the length of the boundary element along the length of the shear wall?
Yeah, already written.
Yeah, this we were discussing also.
Yes.
Theoretically, what it should happen, the concrete can sustain strain up to 0.0035 without confinement. Otherwise, it will spall, it will crack at a strain of 0.0035. In fact, the peak strength is occurring at a strain of 0.002. And at 0.0035, you know, from the stress strain curve, the concrete collapses, concrete fails. So anywhere the concrete is subjected to a strain more than 0.002, you should confine it. Now, question is how to determine that distance at which the concrete strain will be 0.002. So one way of looking at that is what is given in ACI 318, that we know the neutral axis depth, and from the neutral axis, at a particular distance, 0.002 strain will occur, and all the concrete beyond that needs to be confined. That is one way. Our code was having a simpler way where it was saying that in gross section, if you can calculate the stress, and wherever that stress is more than 0.015 FCK, that you consider as this. Another approach is what our revised code is trying to give, that you take it 15% of the length. But that appears to be too simplistic. And as it was presented by Mr. Gokani, that there are issues with that. It may be insufficient in many cases.
Right.
So,
So we definitely need some rational approach to decide the
Rational
length of
approach.
that boundary element. Correct.
I mean, problem is if we go for more rational approach, it will become more complicated. The most rational approach is that anywhere strain, wherever strain is exceeding 0.0002, rest of it should be confined. That is the most rational approach. But there we need to perform a nonlinear analysis, full nonlinear analysis, to determine what will be the strain level in that element under DV or MC. So that's the problem. And whenever we try to simplify, there are some problems.
Okay. The next question is why code doesn't have any clause with respect to beam wall junction checks similar to beam column junctions?
It has now. I discussed today. I have highlighted that the beam column check, beam wall is also to be checked in the identical manner as the beam wall. Same criteria applies there.
Next question is while designing the main beams connecting the columns, we have to follow 20 dB while providing the AST. Is there any way to bypass this clause as far as the width of 300 millimeter beam having a high AST steel provision with 300 by 20 equal to 12 minimum diameter bar is difficult? So what is the importance of this clause?
So I cannot provide anything to bypass it, but I can give you a suggestion to how to satisfy it, practically satisfy it. Perhaps that's what you mean, not bypassing. Nobody has the intention of bypassing. Everybody wants to satisfy it, but there are practical difficulties. So the way that has been given by the code also, I mean this revised code also, that wherever you are having this connection with the beam, you provide a boundary element, a column like element, and that will be designed in the same manner as a column, and that will be part of your shear wall. Design the shear wall taking that column into account, and it will satisfy this connection problem also.
Problem with that boundary element is there are always windows there.
Yeah. We say na, सब कुछ नहीं मिलता जिंदगी में.
Yeah, sir,
So
on that
somewhere
point,
we have to.
sir, on that point, the beams which are framing in the minor direction, can they not be a part of the lateral load resisting system? Is it possible, or that is not possible?
They are, those beams are part of it.
Right.
I mean, making a beam part of lateral load resisting system is easier than not making it part of lateral load resisting systems. Generally, we think that using gravity columns will make designer's life simple. Actually, it's not. Designer's life is not simpler. Designer's life is simpler if all the members are considered as lateral load resisting members.
Yes, you are right. Someone is asking again the similar question, but I think you answered that. Why 0.4 FCK axial stress limit is not added to shear walls in the code? In the present, only it is for the column. I think shear wall also you explained it very clearly.
So revised code has included that for
yes,
sure.
Yes, you explained. Yeah. Now someone is asking why IS 13920 recommended avoiding welding of HYSD bars in RCC SMRF system, which is contradicting with IS 2751.
I'm not aware what is the provision of IS 2751. I'm not aware about that. But why it is not allowing welding is because in welding we do heating, and all our reinforcement nowadays is TMT, thermomechanically treated. And if we heat it, its properties will change. You will not get the same strength and ductility. So that's why welding is not allowed.
Okay. Then the next question is, we cannot release the beams as per the new code. Does that mean beams framing into the wall in minor direction will have to be considered in the earthquake analysis?
Yes, that's what we were discussing just now.
Yes, it has to.
How to take care of that.
Correct. I think similar question again is if 0.4 FCK check for the combined shear wall, shall we need to check for separate pier level or combined pier level? As in both case, axial forces will be different.
Yeah, so actually it is talking about stress. So whatever is the distribution of the force, stress should not exceed this. Axial stress should not exceed if we are doing a finite element analysis. So axial stress should not exceed this 0.4.
Okay, someone is asking why Indian code doesn't have any alternate diagonal reinforcement detailing where the entire beam is confined and omit the links for diagonals only. It is easy to construct and ACI has that option.
Yeah, I agree. So this we can raise to the code committee as part of this wide circulation comments. We should raise that option should also be included in the code. Our codes design provisions regarding shear walls are highly inadequate. So, I mean, one is the issue which we were discussing regarding the envelope, bending moment envelope. Then Mr. Gokani has presented that 1.4 bending moment thing is to be explained more. And then a lot of things are to be done regarding this detailing of coupling beam, like using of steel reinforcement, that should be dealt with the code. Then different types of detailing possible, in which range of shear stress, which modeling is allowed. All these should be given by the code. So we can recommend that the code to take care of. And code can take care of these because these are already available in some other.
Okay. The next question is, does code also require the foundations to be elastic for seismic cases? Because repairing of the foundations cannot be so easy.
Yes, it is intended, but so far code has not included that provision. Actually, there should be capacity design of foundations also, like we are doing in case of bridges. In bridge codes, it is already included, but in building code, it is not included so far. Again, this is also a very interesting suggestion which we can make to the code committee. I guess based on our discussion and further input from our participants and discussion, we will be sending some
Yes, yes.
recommendations to the code committee.
Yes.
So in that we can include these. These are interesting inputs.
Okay. Someone is asking how much is the straight length when the diagonal reinforcement is bent inside the supporting wall.
Okay.
I mean, that should be
So-
development length, at least minimum, what is understood. How much is the straight length he's asking when the diagonal reinforcement?
I mean,
is bent inside the
1.5
wall?
times is the total length. And just now we answered that, yes,
Anything-
bending will be better. So we can do that, but our code does not talk about something like standard hook, which is there in ACI 318, where it specifies what will be the straight length and what will be the bent up length. So
Yeah.
that needs to be specified. Yes.
Okay.
Otherwise, if it is not there in our code, we can always refer to ACI 318.
Again, the similar question, I think you answered that. Can we still release the beam on the minor axis if we cast it
No.
monolithically? We can't
We
release.
can't. We can't. Anything which is constructed monolithically will be analyzed also monolithically.
The next is in the beam column, exterior joint. In many international codes such as ACI 318, New Zealand code and others, the vertical portion of the L bend is limited to 12 times the diameter of the beam. Diameter of the bar, it should be, I think. Longitudinal bar. Starting at that longer extension of the vertical portion is ineffective. But IS 13920 gives no such limitations.
Right. That's what I was referring by that standard hook, 90-degree hook. So in ACI 318, that provision is there. In our code, it is not there. So this detailing at the exterior joint where we are taking LD plus 10.5 into that may not be adequate in many cases. So ACI 318 detailing is different. And that's perhaps his reference.
Okay, then this is regarding dual system. Someone is asking in the definition of dual system, IS 1893 says MF need to be designed for 25% of the lateral load. Can we give the moment frames 25% capacity and take the advantage of dual system, even though the load is not going in the moment frames by inherent stiffness of the lateral system?
Yeah, interestingly, this thing has changed now. I mean, I was also a bit confused here when I was reading this code. Now the code does not define dual system like that. Now the code is defining dual system, something like which is having shear wall and column in the same plane. So this needs to be referred back to the committee that they should clarify what do they mean by dual system and how it is different than a frame shear wall system, which is given as a separate system.
Correct, because the earlier also, even if the shear walls are taking 100% load, you have to design the frame still for 25%. That was, I think, earlier intention.
Right. Whether
That
that
is
is still required or they have relaxed it, it's not clear.
Yeah, that is not clear, correct. So we have to raise that also. The next is in the gravity column for deformation compatibility. Shall we need to do any non-linear analysis with P delta or with R equal to 1? With linear
No, R
analysis,
is equal to 1 ensures that only. So if we do with R analysis, R is equal to 1 and we design those members with R is equal to 1, that takes care of it.
that's enough. Further, international code have considered the concept of horizontal development length when L hooks are provided based on the experimental research. Why no such provisions are there in IS 13920?
I mean, it's the same question which we were discussing earlier. So we have to refer it to the code.
Someone is asking the
This is
email
the
ID
time
of
we should refer.
Dr. Singh. I think Parolekar, you will be compiling this, I think, balance
Yeah, we
question.
will provide that.
And someone is asking about this presentation also, whether you are going to share
Yeah,
this.
we will be, as a normal practice, we will be asking feedback at the same time. After receiving feedback, we will send the presentation also.
Someone is asking, can we use the spandrel in the analysis if it is resting on the minor axis of a wall?
This again, I don't understand what is meant by spandrel.
Spandrel.
Because spandrel is just a beam. It is a
Yes.
deep beam. Only thing is that it is a deep beam. So I do not know. Somebody else also asked some time earlier. So I really do not understand the difference between a spandrel and coupling or spandrel and a beam. From analysis and design point of view appears to be same.
They are same.
Yeah, same. Yeah.
Yes, it's only ETABS terminology.
Now somebody asking when the secondary beam should not be released also.
Yes, secondary beam should also not be released. But we may or may not design our primary beam for torsion. Because when you are not relieving secondary beam, primary beam will have a torsion.
Torsion, yes.
And if you are not designing that torsion, for that torsion, that beam may crack. And if you are willing to accept crack, you can choose that design philosophy, and it is permitted by IS 146.
Okay.
That's all.
I think there are, couple of questions only, last two questions. If the beam rests over one side of the major axis and other on the minor axis of the wall, and similarly, if the beam rests on both sides of the minor axis and L by D ratio is less than 5, then shall we need to design and detail which capacity shear or which diagonal reinforcement? I don't know what exactly it means.
In that case,
On
I
the
would
coupling
suggest
beam,
don't
maybe.
provide beam. What is the need of providing beam? Two shear walls, you have a close distance, and there is a slab at the top, and span of the slab is small. So design the slab as one-way slab. There is no need to provide beam in that case. Don't provide beam. That will complicate.
Sometimes they have to provide beam because there is other side beam resting on that. That is
Oh.
many.
So there are two shear walls, and in between another beam is also running.
Yeah,
and
that is many times the condition with the entry into the lift well. Yeah.
Yeah,
But
real life is
complicated.
really very
Yeah.
tough.
Yeah, it becomes complicated.
Complicated.
So, Arvind, shall we continue or how
Yeah,
much is time?
I think that's all. We just go through the earlier core questions quickly of the earlier people have sent. I think most of them are already
I think those questions
answered.
are
Yeah,
also similar. So
yeah,
we have
yeah.
taken
They
up
are
those.
all similar. I don't think any different is there. One is that have you introduced IMRF? I don't know what is IMRF, sir.
IMRF, this is there in ACI 318 and ESC 7, intermediate moment resistance.
Intermediate. Okay.
So like we have OMRF and SMRF, in between IMRF is also there. Actually, earlier our code before this strong column weak beam design was there, it was actually equivalent to IMRF. So that has been now done away by our code. We are having OMRF and SMRF.
One more interesting question is, can we have variation in ductile detailing based on seismic zones?
Code doesn't say anything.
Yeah.
Code gives only two, either ductile or non-ductile. There is no semi-ductile or IMRF. Perhaps IMRF was something like that. That in some zone we could have gone for IMRF. In ACI 318 it is there, but not in our.
I think that's all. I'll request Mr. Jain Kulkarni to close the session by Jain sir. You are there? Yeah. Yeah.
We have vote of thanks. First of all, I thank all the participants having joined in such a large number. I thank ISSE to be our partner in organizing as well as conducting. And maximum thanks to, naturally, Professor Dr. Yogendra Singh, who always respond to our call for any kind of workshop, webinar, or lecture. And we always look forward for physical workshop with him. And I think it might come only in the month of December. So apart from anything, I thank all the participants, and I quickly summarize what services we offer as Epicons consultant is structural design, proof checking of tall building, structural audits, assessment and NDT, concrete quality monitoring services, project management consultancy, architecture and detail engineering, and of course, training through AFC. So we do conduct programs specifically designed or requested by the participant. With this, I declare that today's session is closed. Thank you, Yogendra. Thank you very much.
Thank you.
Thank you, Kulkarni Saab, and thank you, Epicons team, for organizing this. And thank you, all the participants, for being with us. And hope to see you again, either virtually or physically. So take care. Bye bye.
Bye-bye.
Thank you, Dr. Singh, for a nice presentation.
Thanks a lot, everyone, for the wonderful seminar.